In this video, we're going to talk about the functions e to the x and natural log of x, and also talk about their derivatives. So we'll start by talking about the number e. The number e is approximately 2.71828, but it is irrational, meaning that that decimal expansion never terminates or repeats. And it is defined as e is equal to the limit as n goes to infinity of 1 plus 1 over n to the nth power. So that is one definition of the number e, and so this graph below is illustrating that as we put in larger values for n, the value of 1 plus 1 over n to the nth power gets closer and closer and closer to the true value of e. And so, if we put in 100,000 in for n, we get in something pretty close to what we have up here as our decimal expansion, which again continues forever. So this is one definition of the number e, but there are other definitions that are equivalent as well. And the number e is a really important number in a variety of fields and applications. We're going to see one way that the number e is important in this lecture. So now let's look at the graph of the function y equals e to the x power. For example, e to the 0 is 1, just like anything to the 0 is 1. So when we plug in 0, the output is 1. E to the 1 is just e, is 2.718. So there, or 2.718 dot 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 dot. So there's that. And e to the negative 1 is 1 over e. So 1 over e is right about there. So that's the function e to the x. It's an exponential function. It grows exponentially. And what we're interested in right now is finding the derivative of e to the x. So let's do that using our definition of the derivative. The derivative with respect to x of e to the x is the limit as h goes to 0 of e to the x plus h minus e to the x all over h. So that's the limit definition of the derivative. Now we are going to factor an e to the x out of the numerator of that. So that's the limit as h goes to 0 of e to the x times e to the h minus 1 over h. If you're wondering about that step, remember that in general, x to the a times x to the b is the same thing as x to the a plus b, remember? So for example, x to the 2 times x to the 3, that's x times x is what x squared is. X by itself 3 times, that's what x cubed is. And how many x's are there? There's 5 of them, x to the 5th. So that was x to the 2 plus 3. So that's, in general, a formula that is always true, and it's a good thing to know about exponents. And so the way we used it in the limit over there was that e to the x plus h is the same thing as e to the x times e to the h, and then we were able to factor out an e to the x. All right, continuing forward, this is equal to, well, as h goes to 0, that doesn't do anything to e to the x, so we can factor e to the x out. It's constant with respect to h, times the limit as h goes to 0 of e to the h minus 1 all divided by h. So let's think about what that value is equal to. In other words, what is the limit as h goes to 0 of e to the h minus 1 over h? Well, one thing that's equal to is the limit as h goes to 0 of e to the 0 plus h minus e to the 0 over h. And that right there is the definition of the derivative with respect to x of e to the x evaluated at x equals 0. So what is that? That is the slope of the function y equals e to the x at x equals 0. So let's think about whether we can estimate that to start. Okay, so we're looking at the limit as h goes to 0 of e to the h minus 1 all over h, which we said was equal to limit as h goes to 0 of e to the 0 plus h minus e to the 0 all divided by h. And we further said that that was equal to the derivative with respect to x of e to the x evaluated at x equals 0. So let's take a look at this function, y equals e to the x, and try to evaluate that value. What is the derivative of e to the x at x equals 0? So in other words, what is the slope of that function at x equals 0? So we're drawing a tangent line here, a tangent line to the curve, and let's see, for every 1 that we go over in x, we're going up about 1 in y. So right now we're approximating that as being approximately 1. It is, in fact, equal to 1, and we'll prove that right now. Okay, we are going to show that the limit as h goes to 0 of e to the h minus 1 over h is equal to 1. In order to show that, we're going to do a few substitutions. So first of all, we're going to start by letting y be equal to e to the h minus 1, and that means that y plus 1 is equal to e to the h, and it also means that natural log of y plus 1 is equal to the natural log of e to the h, which is just equal to h. The natural log and e to the something undo each other, so natural log of e to the h is just h. So we're going to plug some of those things in. So this is equal to the limit of e to the h minus 1, that's y. So this is just y divided by, we saw that h was equal to natural log of y plus 1, so ln of y plus 1. And we want to write this limit in terms of y. So observe that as h goes to 0, so as h goes to 0, then y, which is equal to e to the h minus 1, goes to 0 as well, because it is going towards e to the 0. H goes to 0, e to the 0 minus 1, and that's equal to e to the 0 is 1 minus 1, which is 0. So this is equivalent to the limit as y approaches 0 of that quantity. Now we're going to do a trick. We're going to multiply the numerator and the denominator of that expression by 1 over y. And so that gives us the limit as y goes to 0 of 1 divided by 1 over y times the natural log of y plus 1. And now we're going to use a property of logarithms. So our property is that, in general, a times the natural log of b is equal to natural log of b to the a. That is a property that's true for all logarithms of any base. And so this is equal to the limit as y goes to 0 of 1 over natural log of y plus 1 to the 1 over y power. Okay, so we're going to do one more trick here, and our last trick is to substitute y equals 1 over n into this limit. So we'll observe a few things. So as y goes to 0, that means 1 over n goes to 0. As 1 over n goes to 0, that means n is going to infinity, because it's something over a big number going to 0. If 1 over n is going to 0, that means n's going to infinity, or potentially negative infinity. What else? So y is 1 over n. That means that 1 over y is equal to n. So we are substituting into that limit, and we've got the limit as n goes to infinity of 1 over the natural log of 1 over n plus 1 to the nth power. And that is equal to, all right, we know that this is equal to 1 over the natural log of the limit as n goes to infinity of 1 plus 1 over n to the nth power. So we know from properties of limits that we can take the natural log outside of it, we can take the 1 over outside of it, so we're just dealing with everything that's actually changing, everything that has an n in it. And what is that? We said above that our definition of e, or one definition of e, was that e is equal to the limit as n goes to infinity of 1 plus 1 over n to the nth power. So that's exactly what we have inside the natural log. So this is 1 over natural log of e. What is natural log of e? Well, it's the exponent that we need to raise e to get e to the 1. What is that? That is 1. And so we have shown that the limit as h goes to 0 of e to the h minus 1 all divided by h is equal to 1. Okay, so why did we want to do that? That was because we found that the derivative with respect to x of e to the x was equal to the limit as h goes to 0 of e to the x plus h minus e to the x all over h, which we found simplified to e to the x times the limit as h goes to 0 of e to the h minus 1 over h. And we have just proved that that limit is, or that is equal to e to the x times that limit is 1, so that's e to the x. So we have found that the derivative with respect to x of e to the x is itself, is e to the x.